In this session, we will talk about simple resistive circuits. Our first discussion will be about subcircuit equivalence. A subcircuit is referred to as a portion of a circuit. Any two-terminal subcircuit has a terminal law that relates terminal voltage and current, where V is the voltage and I is the current. You can see we have a small circuit. This is the terminal voltage, and you can see we have the terminal current. This is the positive end of the voltage, and this is the negative end of the voltage. You can see the terminal current flowing towards the circuit element. There is a terminal law for a resistor, an independent voltage source, and an independent current source, and for as many circuit elements as possible. For the resistor, our V is always, the voltage is always a function of I, and we know that V is equal to Ri, which is resistance multiplied by the current. Or that can be rewritten if we write our R in terms of the conductance, where our I is going to be a function of the voltage. We do know when R is replaced by conductance, we know our conductance G is usually equal to 1 over R. Hence, our I will be equal to G multiplied by V. The independent voltage source is usually represented as Vs. So the voltage of an independent voltage source is usually represented as Vs, while the current of an independent current source is represented as Is. Vs means V source, Is means I source. If two subcircuits have the same terminal law, it simply means those two subcircuits are equivalent. As we continue to study, we will find out that using simpler equivalent circuits to replace the more complex circuits save time and resources in circuit analysis. Two adjacent elements are in series if they share a common node that has no other current entering it. For example, R1 is a circuit element, R2 is another circuit element. At this particular point, we can say there is a node here. These two circuit elements are adjacent and they are in series because there is only one current entering this particular node that connects both of them together, the current I. So we can say both of them are in series. Also, R2 and R3 are in series because we can say this is a node and there is only one current that is entering this particular node that connects the two circuit elements together. So two adjacent elements are in series if they share a common node that has no other current entering it. Non-adjacent elements are in series if they are each in series with the same element. If we apply KVL that we already discussed in the previous lectures, if you've not gone through the videos of the previous lectures, please do so. We can use KVL and Ohm's law to quickly analyze this simple circuit. We know that when voltages are connected in series, their equivalence is obtained by adding all the voltages together. Hence, we can say that the Vs, which is the voltage source or equivalent voltages of all these voltages connected in series, will be equal to V1 plus V2 plus V3. We do know that our voltage, according to Ohm's law, is equal to resistance multiplied by current. Hence, for V1, we can say that V1 is equal to R1 multiplied by the current passing through it. And that's why we have R1I replacing Vy. The same law applies to V2, which will become R2 multiplied by I, because the same current would also pass through R2, and then the same current will pass through R3. V2 would also be equal to R2I, V3 would be equal to R3I. Since they all have a common current, we can rearrange and then we collect all the resistances together. We have R1 plus R3 plus R1 plus R2 plus R3 all multiplied by I, which is a common current passing through all the resistors. Hence, we can rewrite this equation, we can rearrange this equation and make I the subject of the equation, and that gives us I equal to Vs divided by R1 plus R2 plus R3, where the addition of all these resistances can be given as the equivalence of the resistance, all the resistances that we have in series, and that is written as Rs. Therefore, our I, which is the current, is equal to Vs over Rs. where our Vs represents the equivalent voltage and Rs represents the equivalent resistance. The equivalence is maintained if the resistors are replaced by single equivalent resistance Rs equal to R1 plus R2 plus R3. So in general, what we can come up with, what we can say in general as a standard is that for n series resistors, the equivalent resistance will be equal to the summation of all the resistors in that particular circuit, as long as they are all in series. N would mean any number. We could have 3 resistors, we could have 2, we could have 4, we could have 2 resistors, 3 resistors, 5 resistors in series, or even 10 resistors in series. We add all of them together to find the equivalence. A chain of series resistors is equivalent to a single resistor whose resistance is the sum of the series resistances. Now let's move on to voltage division. What is the principle of voltage division? If we have a simple circuit like this, we can find V1, we can develop an expression to find V1, V2, and V3 using the voltage division method. So you will find out that from the previous discussion, V1 is equal to R1 multiplied by I. And we also said from the previous discussion, from the previous slide, that I is the same thing as Vs over Rs. So instead of writing I, you replace that with Vs over Rs. And then if you rearrange these by bringing R1 up and Vs back, we have Vs multiplied by R1 over Rs. These are the same. These mean the same, so we are just rewriting and rearranging them. Therefore, we can say our V is equal to Vs multiplied by R1 over Rs. So you will notice there's a relationship between this V1 and R1. If you're looking for V1, R1 is going to be at the top here. Vs is the voltage source and it is the equivalent series voltage in the circuit. Rs is the equivalent series resistance in the circuit. Similarly, we can find our V2. You will notice that in this particular case, what has changed right at the top here, R1 has changed to R2 because we're looking for V2. But then Vs and Rs remain the same. The same thing for V3. Vs and Rs remain the same, but we have R3 here. So when we are looking for V2, we have R2 over Rs multiplied by Vs. When we're looking for V3, it becomes R3 over Rs multiplied by Vs. When we're looking for V4, it becomes R4 divided by Rs multiplied by Vs. The voltage across series resistors divides up in direct proportion to their resistances. When we have a circuit like that, we can refer to such a circuit as a voltage divider. Here is a simple example we can analyze together. Reduce the circuit below to 2 equivalent elements and find the current I and the instantaneous power dissipated by the 50-volt source. We have an independent voltage source, which is this 50 volt. We have about 6 elements in this circuit. We have an independent voltage source, which is 50 volt. We have another independent voltage source, which is given as 100 cos 2t volt. We have a 4 ohms resistor, a 10 ohms resistor, a 7 ohms resistor, and a 4 ohms resistor here. These resistors, 4 ohms and 10 ohms, are connected in series. These resistors, 7 ohms and 4 ohms, they are also connected in series. As you can see, there is only a single circuit entering all of the nodes that are applicable to this particular circuit. So we can say all the 6 elements in this particular circuit are actually connected in series. So to reduce this circuit, we have said all the elements in this circuit are connected in series. So if we add everything together, what we have is 4 plus 10 is 14. 14 plus 4 is 18. 18 plus 7 is 25. So for all the resistors in the circuit, the equivalent resistance will be 25 ohms. And that is exactly what we have right at the top here. To obtain the equivalent voltage, you will find out that there is a single current that is flowing through the circuit. When you look at this particular voltage, because it is a voltage source, we expect that current is going to be flowing from region of higher concentration to lower concentration. So we expect that the current from this voltage source is supposed to go this way, while the current from the 100 cos 2t voltage source is supposed to go up here, going from region of higher concentration to lower concentration. So if the current from here is going up, that simply means that current is in the same direction with the equivalent current in the circuit, with the current flowing in the circuit. If they're in the same direction, it simply means this 50 volts is going to have a positive sign. Whereas in the case of 100 cos 2t, we expect that the current, we are going to have a flow from the region of higher concentration. The charge carrier will move from the region of higher concentration to region of lower concentration. And if that is the case and the current through the circuit is clockwise, that simply means they are in opposite direction. So the polarity of this particular voltage is going to be negative. That is why we have equivalent voltage of 50 minus cos 2t. So this is positive, that's why we have 50 here. And then this is minus, this is negative, and that becomes minus 100 cos 2t. That's why we have 50 minus 100 cos 2t here as the equivalent voltage in this particular circuit. The first part of the question says reduce the circuit to 2 equivalent elements. That is exactly what we have done. From 6 elements, we now have just 2 elements. Then the second part of the question says find current and the instantaneous power. If we apply KVL, what we are going to have if we apply KVL to this particular circuit is, since we would draw our closed path, the current will draw a flow in this closed path in a clockwise manner, in a clockwise direction. That would mean that we'll be traversing in that closed path from negative to positive on this voltage source. That would mean this becomes minus 50 minus 100 cos 2t, and that becomes minus 50 plus 100 cos 2t. That's exactly what we have here. Then it becomes plus, since we are flowing in the clockwise direction, this becomes plus 25 multiplied by I, because that's a current that will be flowing through this 25 ohms resistor. So the voltage here will therefore become IR, and that's going to be 25 multiplied by I, and that gives us plus 25I. And since it is KVL, we have said that the summation of all the voltage in that closed part will be equal to 0. So we add everything together and equate it to 0. If we rearrange that, what we're going to be left with is I equal to 2 minus 4 cos 2t amperes. So that's the current in the circuit. In addition to finding the current, we've been asked to find the instantaneous power dissipated by the 50 volt source. So the power dissipated by the 50 volt source, if you are looking for power dissipated, it simply means I need to enter the positive terminal. Don't forget, when power is dissipated, it simply means power is absorbed or consumed. Okay, so since we're looking for power dissipated, it simply means we are saying that power has to enter the positive terminal. In that particular case, our P will be equal to VI. The V is going to be equal to 50 volt. Since we are looking for power dissipated by the 50 volt source, P will be 50 volt multiplied by the current. In this case, what will be I? Our I will not take on a negative value. Why will I take on a negative value? Because power is now being consumed. Okay, this I is flowing in this particular direction, but now that we want to look for power dissipated, it means we are changing the direction of the current. Current is no longer exiting the 50 volt, it is coming into the 50 volt through the positive terminal. It is entering the positive terminal. Okay, so that will now be the opposite of the I that is entering through the negative terminal. Hence, this I becomes minus I. I is exiting the terminal, but if we are going to have to enter the positive terminal of the 50 volt, I becomes minus I for power consumed or dissipated or absorbed. So minus I then gives us minus into bracket 2 minus cos 2t. If you multiply this out and expand the brackets, we will be left with power equal to 200 cos 2t minus 100 watt. Our next discussion will be on parallel equivalent. Two elements are in parallel if they form a loop containing no other elements. All elements in parallel have the same voltage across them. all elements in parallel, we've mentioned this before, all elements in parallel have the same voltage across them. We have this circuit, as you can see. Here is an independent current source. Here is a circuit element with resistor R1, another resistor R2, another circuit element, resistor R3. You can see them having their individual currents flowing through them. We have I1 flowing through R1, I2 flowing through R2, I3 flowing through R3. R1, R2, and R3 are parallel because the current flowing through all of them are different. I1 is not the same as I2, it's not the same as I3. So if different current flow through circuit elements in the same circuit, those circuit elements are said to be parallel. And the voltages across them will be the same. So it simply means the voltage across R1 will be equal to voltage across R2, and that would also be equal to the voltage across R3. So we can represent V1, V2, and V3 with one circuit voltage V, because all of them will see the same voltage. However, if they are in parallel, the current passing or flowing through each of these circuit elements will be different. I1 is not equal to I2 and is not equal to I3. So hence we can represent this equivalent circuit as Rp. Since R1, R2, and R3 are connected in parallel, we can represent the equivalent resistors with one resistor Rp. So this is an equivalent resistance of this entire circuit, and it is called Rp. And that would also be seeing the same voltage. I still remains here. So if we take KCL at node A, there is going to be just a single node here because there is no other element in between R1 and R2 at the top here, no other element between R2 and R3 at the top here. So all these points, this is a node, this is a node, this is a node, this is node 1, node 2, node 3. The three nodes can be represented with just one single node, which is node A, because those nodes contain no other element in between them. Okay, so let's take KCL at node A and apply Ohm's law. Our total I, this I, if we take this as a node, we had said at the beginning that when current is entering a node, we represent it with a negative sign, and when current is leaving a node, the polarity is going to be positive. So this can become minus I plus I1 plus I2 plus I3 is equal to 0. If we rearrange, then we have I1 plus I2 plus I3 equal to I, and that's exactly what we have here. And we do know that our I is equal to GV, where our G is 1 over R. Hence, we can replace all these I's with their respective values according to Ohm's law. Ohm's law states that V is equal to IR and I equal to GV. So instead of writing I1, this becomes G1V plus G2V plus G3V. And then we know G1 plus G2 plus G3 will be the equivalent conductances in the circuit. When you add all of them together, it gives us GP. Okay, so this shows that we have equivalent conductances in the circuit. So the equivalent circuit has a terminal law I equal to GPV. This is the equivalent conductance in the circuit. GP will be equal to G1 plus G2 plus G3. In general, for n parallel resistors, whatever n is, it could be 3 parallel resistors, 5 parallel resistors, 50 parallel resistors. In general, you can say that our GP will be equal to summation of all the G's in the circuit, or our 1 over Rp. We do know G is inverse of resistance, by the way. That's why we can replace GP with 1 over Rp. That means that 1 over Rp will be equal to summation of 1 over Rs of all the resistance in the circuit. So if we have just 2 parallel resistors in the circuit, how do we find the equivalent resistance? What you find here is this. The equivalent resistance of 2 resistors in parallel is the product of their resistances divided by the sum of the resistances. This only applies to a circuit that has just 2 parallel resistors. If we have 3 resistors that are in parallel, we cannot use this formula or use this method. This is a circuit with 2 resistances, R1 and R2. And then we have our current source. The equivalent will be Rp. We had said that 1 over Rp would be equal to summation of all the inverse of the resistances in the circuit. In this case, we have just two of them. So 1 over Rp will be equal to 1 over R1 plus 1 over R2 because there are just two resistances in the circuit. If you rearrange this and you cross multiply, this gives you Rp equal to R1 R2 divided by R1 plus R2. This is only applicable to circuits with two resistors in parallel. The I here does not represent current. The I here represents the number of resistances that we have in the circuit, starting with 1. Since we talked about voltage division in the previous discussion, we can now talk about the current division. We can talk about principle of current division. We already have this simple circuit here, and then we have the equivalence of this circuit. Ohm's law says that I1 is equal to G1V, which will be equal to G1 multiplied by I over GP, because we had said in the previous slide that our V is equal to I over GP in the previous slide. So if we arrange this, we can bring I out, and then this becomes G1 over GP. So this becomes I1 equal to the total I in the circuit, this I source. This I represents the source current. So I1 will be equal to the I source multiplied by G1 over GP. G1 is 1 over R1, GP is 1 over RP. If you carry out simple arithmetic operations on that, you will be left with RP over R1. Hence, we can say I1 is equal to the source current multiplied by G1 over GP, or source current multiplied by RP over R1. And this is applicable to all the other currents in the circuit. Hence, we can say I2 is going to be equal to the source current multiplied by G2 over GP, which is going to be the same thing as I, the source current, multiplied by RP over R2. The same goes for I3. Okay, pay attention to how we are interchanging these. When we are looking for I2, we're going to have G2 right at the top here. Okay, and then this GP will be the equivalent conductances that are connected in parallel. Or we're going to have RP, which is the equivalent of the resistances connected in parallel, divided by R2. Okay, so in any case, it is G2 or R2 that we have. If you are going to use G2, G2 will be at the top, will be the numerator. And then if you're going to use the resistances to make your calculations happen, to complete your calculations, the R2 will be the denominator. Okay, so please pay attention to these explanations. Now, let me quickly call your attention to something. When we were finding voltage, we said that V1 will be equal to R1 over RP multiplied by the voltage source. But in the case of the current, it's going to be Rp over R1 multiplied by the current source. Take note of that inversion there. The current through parallel resistors divides up in direct proportion to their conductances and inverse proportion to their resistances. If we have such a circuit, it is referred to as a current divider. Here is a simple example. Let's quickly check it out together. Find I1 through I5 in the following circuit. I1 is missing, I2 is missing, I3 is missing, I4 is missing, I5 is missing. So we should find all of these in the circuit. We're going to use current divider to solve the problem, and we will start from here. This is the simplest of the circuit without any source in it. This is the simplest of the circuit without any other element attached to it. So we can start from there. You can see we have R4 and then R5. Then we have I4 and then I5. Then we have I3 that is coming in. So I3 that is coming in will act as the source current for this particular small circuit, this sub-circuit in the entire circuit. Hence, if you're looking for I5, it will be I5 equal to the source current, which is I3, multiplied by R parallel divided by R5. Or if you choose to use conductance, it becomes I5 equal to the source current I3 multiplied by the conductance G5 divided by the parallel conductance in the circuit. So if we are using the conductance in this particular case, If you choose to use a resistance or choose to use a conductance, you will arrive at the same solution. You will arrive at the same answer. In this particular case, we are using conductance so that you can have a deeper understanding of what we are talking about. I would encourage you to try to use resistance to carry out this analysis and then compare your answers to the answer you obtain. We are going to obtain by using the conductance. Okay, so I5 will be equal to G5 divided by the parallel equivalent conductance in the circuit. The equivalent conductance in the circuit will be the addition of all the conductances in the circuit. Okay, so that becomes G5 divided by G4 plus G5 multiplied by the source current, which is I3. That becomes G5 is going to be 1 over 2 because we know G is 1 over R, so that becomes 1 over 2. And then the equivalent resistance G4 will be equal to 1 over 1 plus G5, which is going to be 1 over 2. If you find the equivalence of these and then you carry out the simple arithmetic operation here, you would obtain I5 equals I3 over 3. You keep that as equation 1. So once you have done that, you can then go ahead. Don't forget that what you have here, we can find the equivalent of these resistances, these resistors. Once we find that, we're going to be left with these R2 and this R equivalent here. R equivalent of R4 and R5. Don't forget that. And in that case, the source current is not going to be I1 in that particular case. The source current is going to be I1. Okay? So once we do that, we can then go ahead and find our I3. How do we find I3? I3 will be equal to its source current, which is I1, multiplied by the conductance here, which is the equivalent conductance here, divided by the total equivalent conductance of this entire circuit. So I3 will be equal to I1, the source, and then we do know that the conductance of I3 is G3, and G3 is going to be equal to G4 plus G5. So instead of writing G3 here, you write G4 plus G5. Because this is going to be G3. This entire circuit represents G3 once you find the equivalent. So, and that G3 is going to be equal to G4 plus G5. Hence, we have G4 plus G5 divided by the entire conductance in the circuit, and that's going to be G5 plus G4 plus G2, and that's exactly what we have here, G2 plus G4 plus G5 multiplied by the source current, which is I1 coming into the circuit. So when you substitute the value of G4 is 1 over 1 and G5 is going to be 1 over 2. So 1 over 1 plus 1 over 2, that is 1.5. That gives us 3 over 2. And then that's why we have 3 over 2 right at the top here. I1 is still here. Then G2 will be equal to 1 over 4. So we have 1 over 4 plus G4 plus G5. We know G4 plus G5 is what we have as a numerator, and that's the same thing as 3 over 2. So this becomes 1 over 4, which is G2, plus 3 over 2. That's why we have 3 over 2 plus 1 over 4 here. If you simplify these and carry out simple arithmetic operations, our I3 would be equal to 6 over 7 I1. You keep that as equation 2. So once you have obtained this, you can then go ahead and use Ohm's law to complete the entire circuit. What is our I1 according to Ohm's law? I1 according to Ohm's law will be equal to 40 over R equivalent. How is that? I1 is the current coming from the source. So that is the I1 is the current coming from the source. Okay, so using I equal to V over R, we can say I1 will be equal to the V we have because we have only one source voltage here, which is 40 volt, divided by R, which will be R equivalent of this entire circuit. How do we find the R equivalent of this entire circuit? R equivalent will give us 1 over G. R equivalent will give us 1 over G2 plus G4 plus G5 plus the 3 ohms that we have out here. We can call that G1 if you want, all right? And then when you carry out a simple arithmetic operation out, your I1 will be equal to 11.2 amperes. Before we go ahead, let me sound a note of warning. There are several ways to solve this problem. You may decide to use conductances, or you may decide to use resistances to solve this problem. if you are not specifically told what to do in a question, if you're not specifically told to use conductance or to use resistance, you can use any of the methods that is actually convenient for you. You can use G and say, since G is equal to 1 over R, you can convert all the resistances in the circuit to G, and then you use that to solve your problem. Or you can use R and say, since you already have R in your circuit, you just want to use your R, and this becomes your R equivalent. In the case where you want to use G, this becomes I1 equal to 40 volt times G equivalent. If you are going to use G, it becomes 40 volt multiplied by G equivalent. If you are going to use R, it becomes V over R, which is 40 volts divided by the R equivalent. Whether you are using R equivalent or using G equivalent, your answers would be the same. And I would encourage you to try to practice this on your own. Find the G equivalent, multiply it by 40. It will give you 11.2 amperes. Or find the R equivalent, divide 40 by the R equivalent. It would also give you 11.2 amperes. It is easy to find the R equivalent. I already taught you exactly how to do that, how to find R equivalent or how to find your G equivalent. You can easily do that. And then you can substitute into this expression and find your I1. Once you know I1, then it becomes very easy to go ahead and find your I3, because we had said at the beginning from equation 2 that I3 is equal to 6 over 7 multiplied by I1. When you put I1 here, automatically you can find your I3, and that gives us 9.6 amperes. Once you find your I3, it becomes easy to find your I5. Our I5 is I3 over 3. Since we know I3 to be 9.6 amperes, we put that in here, and then we can easily find our I5 to be equal to 3.2 amperes. Once we know I5, we know I3, we know I5, we know I1, every other thing becomes easy. How do we find our I2? Since we know I3, we know I1 coming in. To find I2, we just apply KCL at this particular node. If you apply KCL at this node, current leaving this node will carry positive signs, and current entering this node, I1 especially, will carry a negative sign. So we can say minus I1 plus I2 plus I3 equal to 0. If you are looking for I2, you just make I2 the subject of the expression. So our I2 will therefore be equal to I1 minus I3. And that gives us 1.6 amperes. You apply the same method here. You know I4 is leaving this node. I5 is leaving this node. What is coming into this node is I3. We know our I3 already. So you can say minus I3 current entering the node, plus I4 plus I5 is equal to 0. Okay, if you make I4 the subject of a formula, I4 will be equal to I3 minus I5, and that gives us 6.4 amperes. So that's that about this particular example. Here's another example. Find the equivalent resistance seen by the source in the following circuit. And after that, calculate the value of V. This is V. Okay, so from this circuit, what you can see is that we have an independent current source, 2 milliamperes, and then you can see we have 1, 2, 3, 4, 5, 6. These are 6 resistors connected in this circuit. So what you want to do first of all is to find the R equivalent. That's what would make life easy for everybody. That's what would make this analysis easier. You want to find the equivalent resistance. We always start from the easiest or the smallest subcircuit in the entire circuit. This is the smallest subcircuit in the entire circuit, or the easiest to access in the entire circuit. So starting from here, this is a node. You will find out that the current that enters 5 kilo ohms is the same current that will pass through 7 kilo ohms. So using our series equivalence principle, we can say that 5 kilo ohms and 7 kilo ohms are in series. If they're in series, you just add them together, and that gives us 12 kilo ohms here. Okay, so if we have 12 kilo ohms here, you will notice that the current that enters these 12 kilo ohms is different from the current that enters these kilo ohms. When the current coming from this side of the circuit gets to this node, it splits. A portion of it flows down, and a portion of it flows to this other end. So that simply means whatever we have on this end as 12 kilo ohms will be in parallel with these kilo ohms, because the current flowing through both of them are not the same. So that simply means 12 kilo ohms is in parallel with 6 kilo ohms. And since we are dealing with just that small sub-circuit, and we have just two resistances we're working with, the R equivalent for this particular side would be 12 times 6 divided by 12 plus 6. That method is only used when we have two resistors that we are dealing with. Okay, so if we do that, 12 times 6 is 72, 12 plus 6 is 18. That gives us 72 divided by 18, and that is 4 kilo ohms. The entire circuit you see here can be represented with 4 kilo ohms equivalent. Okay, so let's see exactly what is going on. You will find out that the first thing we did was to convert 5 and 7 to find the equivalence of 5 and 7. That gave us 12 kilo ohms, and then we went ahead to find the equivalence of 12 and 6. That's why we say 12 times 6 divided by 12 plus 6, and that should give us 4. Once we have 4, what we'll have next is that there will be 4 kilo ohms here as the equivalent. So you will notice that 3 and 8 are also in series. So you add 3 and 8 together, and that gives us 11 kilo ohms. Hence, the current entry 11 kilo ohms will be equal to the current coming to this entire circuit here, because we have converted 12 and 6 to 4 kilo ohms. So that same current will be the same. So we can say that 11 kilo ohms and 4 kilo ohms, which is the equivalence of 12 and 6 kilo ohms in parallel, the current passing through 11 and that 4 kilo ohms would be the same. So we can just add them together. So we are going to be left with 11 plus 4 as the equivalence of 11 kilo ohms and then this entire circuit here. So we have 11 kilo ohms plus 4, and then we have 10 here. Again, you will then find out that this 10 kilo ohms and 11 plus 4 kilo ohms, which is 15 kilo ohms by the way, are now in parallel, because current coming here, when the current gets to this particular node, that current is going to split. A portion of it will flow downwards to 10 kilo ohms, another portion will flow towards this 15 kilo ohms here. Hence, we can say these two circuit elements or these two resistors are in parallel. If they're in parallel, the equivalence would be this 15 multiplied by this 10 divided by 15 plus 10. That is 150 divided by 25. 150 divided by 25 will give us 6 kilo ohms. So you will find out that we have reduced this big circuit, this complex circuit, this circuit that looks complex, to something very small with just two elements. Independent current source remains 2 milliamperes, and then the resistances in the circuit, the equivalent resistance will now become 6 kilo ohms. With these, we can do anything we want to do. The first thing we want to do is to find the equivalent resistance according to the question, which we have done. Then the next thing we have to do now is to calculate this V here. This voltage will be equal to the voltage seen by this resistance. What is the voltage seen by this resistance? That voltage will be the current passing through this resistance multiplied by its resistance. Okay, so V will therefore be equal to 2 milliamperes, which is the current, multiplied by 6 kilo ohms according to Ohm's law, which says V equals IR. Hence, you can say R equivalent is 6 kilo ohms, and using Ohm's law, our V will be 2 milliamperes multiplied by 6 kilo, and that gives us 12 volt. Hence, the V we are looking for would be equal to 12 volts. Here is another example we can quickly go through to solidify our understanding. Find the equivalent resistance seen by the source in the following circuit, and after that calculate I. If you look at this circuit, you will find out that we have 5 resistors and then a voltage source in the circuit. You will notice that when the current is coming from the voltage source and it gets to this node, when the current gets to this node, it splits into two. A part of it goes to the left and a portion of it goes to the right. Let us consider the portion that comes to the right. The portion that comes to the right goes through 45 and then gets to this node and then goes through 30. So we can say the same current that goes through 45 ohms will go through 30 ohms. Hence, the 45 ohms and 30 ohms resistors are connected in series. If they are in series, it simply means we can simply add them together to know the total resistance that is on this right hand side. 30 plus 45 gives us 75. Okay, so we have 75 here. For the left hand side, as the current gets to the node and splits to the left, it will pass through 40 ohms resistor and then goes through the 50 ohms resistor and then goes through the 60 ohms resistor. So exactly the same current that passes through, that flows through 40 ohms resistor will flow through the other resistors in the circuit. It simply means we can say that these three resistors are also connected in series. Hence, their equivalence will be 40 plus 50 plus 60, and that should give us 150 ohms. So we have 75 ohms, and then we have 150 ohms on either side. So we have 150 ohms here and 75 ohms on the right hand side. If you look at this critically, what you would find out is that the current from this node, the current flowing through 150 ohms equivalent resistance is different from current flowing through 75 ohms equivalent resistance. So since the currents are different, it means they are connected in parallel. Hence, we can use our parallel equivalence calculation method to deal with this for two resistors connected in parallel. It becomes R1 multiplied by R2 divided by R1 plus R2. And that's going to be equal to 150 multiplied by 75 divided by 150 plus 75. If you do that, what you would obtain is going to be 50 ohms. So that is why at the end of the day, you find that we have 50 ohms here, and then we have our voltage, which is the source voltage, still here untouched. So this equivalent circuit with the 1, 2, 3, 4, 5, 6 circuit elements can be reduced to a simple circuit with just two elements, the voltage source and the equivalent resistance in the circuit. All right, from this particular level, everything becomes very easy. We can easily find our I since we already found the equivalent resistance, which is the first question we were asked to deal with here. And then the second is to calculate I. I is equal to V over R, as we know, according to Ohm's law. I is V over R, and our R is going to be the R equivalent, 50 ohms. Our V we also know is 50 volts. But then what is going to be the polarity of our V? We had said right from the beginning that the polarity of the voltage is usually determined by the flow of current. So current is supposed to flow from the region of high charge carrier to the region of low charge carrier. So it's supposed to flow from positive and then out through the circuit element back to negative, and then keeps flowing that way. However, you will notice that the current is not leaving the circuit from positive to negative. You will notice that the current is actually leaving from the region of low concentration and then going through the circuit to the region of high concentration. So the polarity is going to change. In the first case, it's supposed to leave from the region of positive, high concentration, high charge, high concentration to low concentration, but now it is leaving from region of low concentration, going to the circuit element and then back to region of high concentration. In this particular case, the current is going to be negative. Hence, we can say our I will be equal to minus V over R. In that case, this is what we are going to have. It becomes I equal to minus V, which is 50 volts, divided by our R equivalent, which is 50 ohms, and totally that gives us minus 1 ampere. Make sure you go over this example again and again and understand the use of the polarity, how to find the equivalent resistance in the circuit, and how to find the voltage and the current connected to the circuit. Let's quickly talk about measurement devices. An ideal measurement device does not disturb the circuit it is validating or characterizing. So when we have a measurement device, whether the ammeter, voltmeter, ohmmeter, whatever it is, it doesn't affect the circuit, it doesn't disturb the circuit, it just validates or characterizes whatever you want it to characterize or validate, and then that's it. So we have the first one is the ammeter. An ammeter is used to measure current flowing through its terminals. An ideal ammeter has zero voltage drop across it. That simply means it has very low impedance. It has low impedance, and it gets connected in series with the component it is trying to characterize. The next is the voltmeter. The voltmeter is used to measure the voltage across its terminals. Okay, across its terminals. An ideal voltage has a terminal current of 0. That would mean high impedance. When the current is 0, it means high impedance. When the impedance is high, it simply means current cannot flow through the resistance. The impedance is an equivalent of resistance when we are dealing with our resistive circuit here. So it simply means when that is high, the current cannot flow through. Hence, the current flowing through that circuit element of that terminal is going to be equal to 0. It gets connected in parallel to the component it is trying to characterize. Then the next one here is the ohmmeter, which is used to measure the resistance connected between its terminals. An ideal ohmmeter delivers zero power to the resistance it is measuring. It gets connected in parallel to the component it is trying to characterize. How do we use the color code of resistors to know the values of the resistors? We have different types of resistors. Some resistors have 4 bands and some resistors have 5 bands. When you look at the 4-band code resistors, what you will find is that we have the first band, which is A, second band is B, third band is C, and then we have the last band, which represents the tolerance that we have. Okay, so one of the things I want you to pay attention to here is this. The bands are usually closer to one edge than the other edge. So when the bands, you look for the edge that the bands are closer to, that most of the bands are closer to, that is where you start your counting from. You will notice here that most of the bands are closer to this edge. So from this edge, that means this purple is going to be your band 1, then it's going to be your first digit, and then your red band here will be the second digit, the green band will be the third, and then the tolerance would be, and then the yellow band would be the fourth, representing the tolerance. Okay, this expression is very important. Once you know how to analyze the bands and then the digits, you know which one is first. The next thing is you want to use this formula to find the resistance of that particular resistor. R is usually equal to 10A plus B multiplied by 10 raised to the power C plus or minus percentage tolerance. And if you look at what we do have here, you already know the value of A from this band. There is a table I'm going to show you now where you know the values, these values depending on the colors they represent. So you just substitute value of A to here, B to here, C to here, tolerance here, and then U. And then that's it, you find your resistance. Every component has a tolerance. When you have a good design, such designs can tolerate variations. So this is the color code for carbon resistors. So we have the 4-band code, and then we have the 5-band code at the bottom. For the 5-band code, you will notice we have first band, second band, third band, fourth band, and then the 5th band. And notice most of them are closer to this other end here. So you start counting from here. Then this is the 4-band code. You see that most of them are closer to this edge. So you start counting from here. We have 1, 2, 3, and 1, 2, 3, and 4. Okay. So what you will find here is for the 4-band code, the first band is green. So you come to the first band and you look for color green. This is green. So that simply means this first band here is going to be 5. The value for A is going to be 5 in this expression that we give. A is going to be 5. You will notice that the second band is blue. You go to the second band column and then you find blue. You see that this is 6. So you put 6 here. So this is 10 times 5 plus 6. That is 56 already here. Multiply by 10 raised to power C. What is our C? C represents this yellow for the 4-band code. You go to the multiplier and then you look for the value of C. You put it here, plus or minus the tolerance, which we do have here. And then you can easily find the value of your resistance. In this particular case, you can see we have 50. You can see we have 10 times 5, which is 50, plus 6, which is 56 already. All right. And this 56 multiplied by 10 raised to power C. C is yellow. So if you come to yellow here, you see we have 10 kilo ohms here. We have 10 kilo ohms. So this is 10 raised to power 10 kilo ohms. All right. So 556 times 10 raised to power 10 kilo ohms. That would mean that we have 56 times 10, that's 560 kilo ohms at the end of the day, plus or minus 5%. This brown, if you go to the tolerance, you scroll down, look for brown. This is brown. So the tolerance is going to be plus or minus 5%. So the value of this particular resistance of this resistor will be 560 kilo ohms plus or minus 5%. Okay. So for the 5-band code, you can work on that too. This is the expression you use for the 5-band code. It's going to be 100A plus 10B plus C multiplied by 10 raised to power D plus or minus the percentage of the tolerance. So for these, try to find out what the resistance for these would be. It's been obtained here to be 237 ohms plus or minus 1%. All right, let's take it a step further. We have some other measurement devices we might want to quickly look at. We have the digital meters and we have analog meters. For analog meters, current in coil creates torque under the magnetic field, causing it to rotate together with an attached pointer across a calibrated scale. Okay, so you can see the pointer here, and you can see the magnetic steel core. Here you can see the permanent magnet. This is a magnet here. You can see our various scale here, basically. Okay, so, and then this is what is going to be inside here. All right, so this measures the milliamperes. When we have 1 milliamperes, the voltage drop is going to be 50 millivolts. That's what that means. Then again, we have the digital meters. The digital meters are the most common kinds of meters that we have in the world today. They measure analog signals at discrete points in time, convert it to digital form. They in general have less resistance than the analog meters, and they are easier to connect and have higher precision due to the readout mechanism. If you go to most of the modern laboratories we have today, like the one we have in the school here, if you go to the laboratory, you will find out that what we have is the digital meters. So you should use them, practice them, and be able to apply them to your experiments. Quickly, we should look at resistance measurement through Wheatstone bridge. Resistance measurement through Wheatstone bridge. When you see a circuit like this, it is called a Wheatstone bridge. You can see right in between point terminals A and B, you can see we have a galvanometer that is used to measure current. And then you can see we have a kite-like shape here, a diamond-like shape. And then you can see we have the terminals at the top and the bottom of the circuit connected to a single voltage source here. Okay, and then at this particular terminal, you will find out that the current will split into two. So you have a current I1 moving in this direction to the left and current I2 moving in this direction to the right. I1 flows through R1 and then I2 flows through R2. Again, you will notice that from this particular terminal, we have from the terminal A and terminal B, current flows down to these last terminal at the bottom here. That gives us, and that current is I3 passing through R3, and then we have another current flowing down here called the IX passing through RX. The IG you see here is the galvanometer current. So when you get to the lab, you will be taught how to create a Wheatstone bridge circuit, and then how to connect a Wheatstone bridge circuit, and how to find RX. You find RX when you are able to make sure the current flowing through the terminals A and B, between these two terminals, when the value of this galvanometer reads 0. When IG reads 0, then you can find your RX. And when that happens, there is a simple formula that you use. What Wheatstone bridge does is that it helps us to find the value of an unknown resistance using known resistance and variable resistance. You keep varying the value of this R3. The more you do that, the more the current through this galvanometer changes. You keep varying this R3 until IG is equal to 0. When that happens, you will be able to find the value of R. Okay, so there's a simple formula that you can use. You keep adjusting R3 until IG is 0 as measured by the galvanometer or ammeter in the center. So applying KCL, once IG is equal to 0 and you apply KCL, that simply means that the current flowing through this branch of the circuit will be the same current flowing through this branch of the circuit, because we had said that this IG would be equal to 0. So current cannot flow through this branch anymore, since we have varied R3 so large that current cannot flow through this branch anymore. So when that happens, I1 will be equal to I3, and then I2 will be equal to IX. So you keep those two equations. VAB will be equal to 0 when the bridge is balanced, because our IG is 0. We know V equal to IR. If I is 0, that simply means V will be equal to 0. So IAB, which is equal to IG, would be equal to 0. VAB would also be equal to 0. So that's why we have VAB is 0 when bridge is balanced. So when you vary R3 and you're able to accomplish your Ig to be equal to 0, that means the bridge is balanced. There are cases when the bridge is not balanced, and then you will still need to, simplify, analyze, and work on the circuit. Okay, if it's important, we're going to talk about that. But that is not what we're talking about right now. Now we're evaluating a circuit that is balanced. Okay, so if you apply KVL to this circuit, what you will find out is that I3, the voltage across this R3 will be I3 R3 will be equal to, because this is a closed path, you can create a closed path here. So the voltage across R3 will be I3 R3 will be equal to voltage across Rx, which is Rx Ix. Why is that? That is because if you want that happens because we have this a closed path. If we have a closed path here and current is moving this way, so what you will find out is that this current is 0 plus Ix Rx minus I3 R3 equal to 0. Since this is 0, we are left with Ix Rx minus I3 R3 equal to 0. Hence, our Ix Rx will be equal to I3 R3. That's exactly what we have here. The same principle is applicable to this path, this closed path. So our I1 R1 will be equal to I2 R3, applying KVL principle. By the way, this is just mathematics, so you can solve these equations 1 to 4 the way you want. Well, the most important thing is that when you are solving the equation, you make Rx the subject of the formula. Eliminate all the currents. Okay, you find the way to solve for Rx by eliminating all the currents here. So to do that, when you do that mathematically or arithmetically, you obtain Rx equal to R2 multiplied by R3 all divided by R1. This can also be written as Rx R1 equal to R2 R3. And if you come to the circuit, this is what it looks like. Where is Rx? This is Rx. So you can say Rx multiplied by R1, the opposite resistors, is equal to R2 multiplied by R3, the opposite resistor. So if you do that, you can easily find your Rx. Or you can say that R3 over R1, that is, where is R3? This is R3 and this is R1. So these are adjacent, not opposite now. These are adjacent resistors. So you can say R3 over R1 would be equal to Rx over R2. Okay, so whatever it is you want to do, these are simple ways to remember this formula, and then you can make Rx the subject of the formula and find that unknown resistance. So a wide range of Rx values can be measured by making R2 over R1 coarsely adjustable and R3 finely adjustable. Normally R2 over R1 can be varied between 0.001 to 1000 with 10x steps. R3 is adjustable between 1 ohm to 11,000 ohms. This is where we will end this particular session. Don't hesitate to subscribe to this channel in case you are yet to do so. Also give this video a thumbs up if you like it. I look forward to reading what you think about this video, what you think about this analysis, what you think about all the circuits that we have discussed in the comment section. Thank you and see you in the next session.